for even with the current hardware, you can outperform some classical solvers. I'm not claiming all the classical solver, whether it is the best or not. And for this problem, hierarchy and constraint, what is the best is still a question itself. So the two algorithms that we compare are, one is an exact solver. That's not a fair comparison, as you mentioned. And the another one is a heuristic solver, that is CPLEX and simulated annealing. So to start, I will start by introducing our algorithm itself. So that is digitized contradiabatic quantum optimization. So the inspiration comes from adiabatic quantum computing. So as you might know, in adiabatic quantum computing, given a computational problem, you encode this problem in some many-body Hamiltonians. So the optimal solution to this problem is usually encoded in the ground state of this many-body Hamiltonian. In order to find this ground state, what you do is you start with some initial Hamiltonian, Hi, and then you slowly interpolate towards the final Hamiltonian. And the total Hamiltonian is given like this, where lambda is some what you call scheduling function, so which basically describes the path, how you go from your initial ground state to the final ground state. And the runtime of adiabatic quantum computing mostly depends on something called minimum gap. So during this evolution, starting from the initial ground state to the final, somewhere during this evolution, you will see that the gap between the ground state and the first excited state, what we call this instantaneous energy spectrum, is drawn there. So the gap between the ground state and excited state becomes minimum at some point. And this tells you what is the runtime of the algorithm. And typically, as you increase the system size for some complex problem, this gap becomes smaller and smaller. In many cases, it's exponentially smaller. So the runtime is also exponentially, especially if you're talking about some problems that are NP hard, let's say. So the question is, how can we run this on current quantum hardware? The current quantum hardware has limited coherence time, so the qubit die after a certain time, so you have to finish your computation in a given coherence time. So typically what people in the quantum annealing community do is that they do not rely on this adiabatic condition. They do not evolve the system slowly. So rather they evolve it very fast. That will result in excitation. So you will no longer stay in the ground state. So there will be some excitation to higher energy states. That means the quality of the solution reduces. The ground state success probability, or the probability of getting the optimal solution, decays. The faster you move, the excitation probability is larger. So, but the solution, what they do is that they take many samples. So they repeat the experiment many times, and they look for, okay, can I find the optimal solution or even suboptimal solution once? So even if you find it once after 100,000 times, so you solve the problem. That's okay, but the question is there a way where we can evolve the system faster, at the same time we can minimize the excitation between the higher energy states and the ground state? And there comes this concept called contradiabatic protocol. So the idea of contradiabatic protocol is that you have this fast moving Hamiltonian, that's HAD, and then you introduce an additional term that helps you to suppress this excitation between the ground state and the excited state. So in principle, if you can find this term exactly, you can completely minimize the excitation. So you always stay in the ground state. But the problem with this method is that finding this contradiabatic term is extremely hard. So even finding itself is exponentially harder for complex problem. And even if you find it, implementing this experimentally will take you exponential resources in most of the cases. So how about we do not rely on this exact method? Why not approximate it? And there comes this paper in 2017 by Demeric Park and not Demeric, it's by Polkovnikos. They've come up with an approximate method. Instead of completely suppressing this excitation, they propose a method where they partially suppress it. It's called approximate contradiabatic methods. So that is actually kind of a eureka moment for us. And I was working on my PhD thesis, and I was trying to solve this basically ground state preparation problem. And I came across this paper, and I thought, why not use this technique for optimization? So that's how we developed this concept called digitized counteradiabatic quantum computing. So before going to that, so this counteradiabatic protocol can be, you can think of it like a waiter delivering, water to the table in a tray. An adiabatic way of doing this is very slowly move, and you can deliver, but it's inefficient. So you have to be very slow, and he loses the tip. You want to be faster. And non-adiabatic way is you move faster, and you might spill the water, and that's also not good. And the counteradiabatic way is you tilt the tray in such a way that you can move faster, as fast as you want, if you're good enough, and then you can deliver the water without spilling anything. So that is the idea behind this counteradiabatic protocol. So introduce an additional term that helps you to suppress this non-adiabatic excitation during quantum annealing. Then we took this. So this is a continuous evolution. We have the theory. So we have the recipe to design a way to find the final ground state, that is the solution to our optimization problem, and how to realize this in practice. And that we propose this concept called digitized counteradiabatic quantum computing. So we have the continuous evolution given by this Hamiltonian, where A lambda is something called this adiabatic gauge potential, or justly the counteradiabatic term. And this can be written as sum of nested commutator, and where L determines the order of expansion. As L tends to infinity, you will get the exact counteradiabatic term. So you can tune this parameter depending on how much accuracy you need. So throughout this talk, whatever I talk is L is equal to 1. That is, we just consider the first order approximations. So once we have this Hamiltonian and we have the time evolution operator, what we do is we discretize this evolution into smaller chunks. We discretize it in time. Then you end up with unitaries at each delta t. And this unitary can be decomposed into 1 and 2 qubit unitaries, so that you can realize this on a digital quantum hardware. So there is many other reasons behind why we propose this digitized counteradiabatic protocol, because it gives you a lot of flexibility, and current quantum annealers cannot realize these counteradiabatic terms because of something called non-stochasticity, which I will not go in detail. So basically, realizing this counteradiabatic protocol on analog quantum computer is extremely difficult. So that is one of the main reasons we went for this digital counteradiabatic protocol. Recently, what we thought is that, so in digitized counteradiabatic protocol, basically you start in the ground state of some initial Hamiltonian, and then you do this trotrized evolution with the counteradiabatic term. And one thing I forgot to mention is that, as I mentioned, you can do this fast evolution by introducing this counteradiabatic term. And this fast evolution in the language of digital quantum computing is nothing but reducing the overall circuit depth. So the CD protocol gives you a very short depth quantum circuit, but retaining the accuracy of the solution. But still, there is one problem now. As you increase the system size, the excitation probability is exponentially large. I mean, it is larger. So only considering first order nested commutator is not enough. So we come up with a protocol for that. So instead of starting with one initial ground state, do the evolution and measure, why not repeat this process again and again? So initially you started with some initial equal superposition state. Then you do the evolution, measuring the computational basis. And this solution is better than what you started with. Why not take this and put it back to the initial state, so that in the next iteration, you're starting in a much better state, which is much closer to the optimal solution. So this is an iterative process that we call bias field digitized counteradiabatic quantum optimization. Here, bias field means you are biasing your initial state towards the solution, and this is purely non-variational approach. As you know, there are many variational quantum optimization protocols, like QAOA is one, where you have to tune your parameter. You have to find the optimal set of parameter that gives you better solution. This requires huge classical computation overhead. And in many cases, if you have noise, there is something called noise-induced barren plateaus. And it becomes very difficult to find the optimal set of parameters. We completely avoid that process. We just measure in the computational basis. We take many, many shots. Let's say you took 100,000 shots. And out of this 100,000, you get a distribution of solutions. You only focus on the low energy part that is relevant and use this information to construct, start with a better initial state for the next iteration. So iteratively, you are refining and going towards the optimal solution. And all the parameters in the circuit are calculated analytically. So there is no tuning overhead in this case. And another thing is that the way how we chose the set of what you call post-selected the solution is based on what you call this conditional value at risk, or CVAR, which has some robustness against noise. That means even if you run 10,000 times and you find the solution only a couple of times, and you are using this to bias your next iteration, still it gives some kind of, it actually improves the quality of the solution, even in the presence of noise. And the scalability is another feature of this algorithm because there is no variational tuning of the parameters. It is just analytical calculation. And also the algorithm has some robustness against hardware noise. And we also did a lot of benchmark previously. And we wrote several papers on this concept in the last 2-3 years. And we did a lot of benchmark for different instances and different use cases, comparing it with other quantum methods like quantum annealing or quantum approximate optimization algorithm. And we do have it as a solver available in IBM. What we call is Sky Quantum. It's a solver. You can just go there and you can start using it. And if you want to try the trial version, it's also available in our platform called Planck. So we are already developing a product in this direction. In this one, if there are no questions, I will now discuss about the main topic of this talk, that is runtime quantum advantage. So we have the algorithm now. I described this, the algorithm we consider is an iterative digitized counter-diabetic quantum optimization called bias field DCQ. And how do we choose the instances to show this runtime quantum advantage? So there are some recipes before showing quantum advantage. So first thing is we need hard instances where we want to benchmark. The second thing is these instances should be realizable on the current hardware. Everything that is reported is from the current hardware of IBM, 156 qubits. So how to design the instance or how to find the instances that are hard for classical, and what are the metrics that has to be considered while comparing the performance, and also the problem instances depends on the coefficients. How do you choose it? So what we did is we consider, as I mentioned earlier, the problem that we considered is the higher order unconstrained binary optimization. So it's an extended version of QUBO. In QUBO, what you have is a quadratic term. Here we go beyond quadratic. We have cubic term or fourth order term. But in this example, we consider it's a cubic term with around 400 plus cubic terms for in our Hamiltonian that we consider. And this Hamiltonian was designed in such a way that you can utilize the hardware fully, in a sense that, as you know, IBM quantum devices have sparse connectivity. It's what they call this heavy hexagonal architecture. If you have interaction between, let's say, qubit 27 and 98 in your problem Hamiltonian, then it is very hard. You have to use a lot of swap operation. This is like a waste of resources. So that's why we come up with a clever way of constructing the instances. So we start with the hardware itself. So we take the hardware as it is, and we see what are the nearest neighbor interactions that is available, and we construct one set. And then we apply a set of swap operation. That means you are changing the qubit's position. Now we end up with another set of interaction terms, and we do it multiple times. So this is what we call number of swap layers. So as you increase the number of swap layers if you continue like this, you will end up with a fully connected graph. In this case, fully connected hypergraph. But it's too much for the current hardware given the coherence time, so we reduce it to only 2 or 3 swap layers only. And this is how the Hamiltonian terms are constructed. The second thing is how to choose the coefficients. So you have the terms now and how to choose the coefficients. If you choose some Gaussian distribution or some uniform distribution, these problems are easy to solve for classical solvers, especially Cplex, simulated annealing. They can find a solution very, very fast. And we look for other distributions, what we call here Cauchy and Pareto, and these were kind of difficult for these classical solvers that we consider. And we are also analyzing many other distributions that are relevant to industrial problems. But in this paper, what we consider is the coefficients are chosen from this Pareto and Cauchy distributions. And the third thing is the metric. How did we consider the metric to show this runtime advantage? So the metric of interest in this case is time to approximate solution. Rather than time to exact solution, time to approximate solution is the metric that we consider. The reason behind is that the current quantum hardwares are noisy. Even a single bit flip can take you away from the solution. So it is better to focus on approximate solutions. So that's why we chose this as a metric. And as you know, the current classical chips are very, very fast. They work in gigahertz, even more than that. The frequency, the number of samples that you can extract from this classical processor is much, much higher than classic quantum computers. Quantum computers, at most, the current ones operate in the regime of kilohertz, like 10,000 samples per second. That's for IBM hardware. But this is what it is. We have to consider into account. So even though there is a sample advantage, the number of samples that is required to reach the optimal solution for quantum is much lower than classical. We cannot directly claim any kind of advantage right now because we have to consider into account that sampling from classical hardware is much faster. And finally, we benchmark with 2 solvers. One is Cplex, and the another one is heuristics, simulated annealing. The choice is, because we contacted 2 people. One is we contacted people from Google. They said they have been benchmarking with Cplex, and they have one of the best simulated annealing, and they have one of the best implementation of simulated annealing using C++ that can generate around a few 100 million samples per second on a CPU and even billion samples per second on a GPU. So that is one of the reasons we went for this simulated annealing. So that was the suggestion from them, and we consider that as one of the solvers. And then we talked to IBM people, and they said, have you tried Cplex? Cplex can also give you not just the exact, you can also define the optimality gap, and you can also look for this approximate solution. So these are the 2 classical benchmark that we did. And the hardware that we consider is our clusters. It has 48 cores, and the operation frequency, you can find it in our paper here. And for the Cplex, we didn't see any advantage going beyond 10 cores. So after it finds around 8 or 10 cores are optimal. Beyond that, we didn't see any advantage of using multiple cores for them. But simulated annealing can exploit multi-cores. And this is what we are reporting. So as you can see, here we plotted, so these are all experimental results for the bias field DCQ and compared it with Cplex. And as I said, there is no tuning in our case for the quantum algorithms. And we are mostly considering the runtime of the hardware, assuming the number of shots that you can take in the range of 10,000, which is a realistic number for the current hardware. But there are other few things that, as mentioned in the previous talk, once you send a quantum circuit to a quantum hardware, it has to be converted into microwave pulse. So it requires some small time. This is not considered in this benchmark because we don't have control over this time. The conversion of the circuit from circuit to a microwave pulse, this we don't, and it's I guess it can be done faster. So we neglected that time. The second thing is the transpilation time, because we have a circuit and we do the transpilation, and which is kind of negligible in this case, can be done very fast for the, that's why we didn't consider that also into account. Apart from that, all the classical pre-processing, classical post-processing, and the quantum runtime all has been considered in this comparison. So what we have plotted here is that increasing system size, starting with 80 qubits up to 156 qubits, and we reported the time to reach certain approximation ratio. That's what we call time to approximate solution. And compared to Cplex, we see a clear advantage for many instances that we checked. And on the right side, what we plotted is the time to reach this certain approximation ratio of 96% for different approaches. So the dotted line is bias field DCQ, and we have Cplex as well as simulated annealing warm-started Cplex. So yeah, in all the case, we see clear advantage. And we also compare the performance with simulated annealing, and you can see the performance, and also the experiments were repeated many, many times on the quantum hardware also. That's what we reported here, the trial versus the approximation ratio, and you can see in many of the, almost all the cases except one, we see clear advantage over simulated annealing. And this is the result from almost 1 year, and we have an upcoming paper, will be published very soon. And there we talk about not just the time to approximate solution, also time to exact solution, and compare with some exact solvers. Not just Cplex or simulated annealing, we also consider tabu search, memetic tabu search, and some other genetic algorithms also. And that's with the comparison with the existing quantum solvers. How these instances compare to classical solvers, how these instances compare to quantum solvers. So if we consider two quantum solvers, one is quantum annealing, that's on the D-Wave, the latest hardware with 4,000 plus qubits. And the problem is Hubo, and the D-Wave cannot tackle Hubo directly. One has to transform it into qubos and then tackle it. So that introduces an extra overhead of qubits. And that is one of the quantum solver that's run on analog quantum computer. And the another one is what we call, what is proposed in the literature is a linear ramp QAOA, where there is no tuning of the parameter, the scheduling is fixed. So we compare with both the approaches, and there is a clear advantage compared to quantum annealing in terms of qubits, as well as runtime, as well as quality of the solution. And compared to linear ramp QAOA, there is a clear advantage in terms of circuit depth, as well as runtime, as well as the quality of the solution. And we have written 2 blocks on this. You can just scan it and you can find it. And this is actually from the paper. And what are the advantages? So the next slides will be about mostly what are the applications of this higher order binary and constraint optimization problems. So these Hubos appear in many cases. Many classical industrial optimization problems, it is better to map it into Hubo than Cubo, because it saves you a lot of qubits. It comes with less overhead. And that's why we are mostly benchmarking all of our works are mostly on Hubo because of that reason. And one such example is protein folding, which is mapped to the problem is defined on a tetrahedral lattice. Usually protein folding is done in free space, but that's how AlphaFold works. But for the quantum computers, currently the existing mapping, one of the mapping that we consider uses this tetrahedral lattice structure, which is not that realistic, but we are improving upon it, and it can be used as a warm starter for classical solvers. So anyway, so this is the work that we done with IonQ, and we consider their 36 qubit hardware with 10, 11, and 12 amino acids, and it's up to 33 qubits. And we were able to find ground state, that's the optimal configuration for all the 3 cases that we studied with this bias field DCQ approach. And yeah, this is just a small animation. Yeah, you can find this work in, it's in archive now, and we are also continue collaborating with IonQ, and there will be more news regarding even larger proteins. And yeah. The second example that we that maps to Hubos natively is this LABS, low autocorrelation binary optimization problem. This was the work that we done with quantum optimization working group. It's by IBM and many other institutes and industries. We have a group and it's around 70 plus people. And there we listed some of the hard problem instances where classical solvers struggle. And one of them is a low autocorrelation binary sequence problems. For this problem, the best optimal solution is now till 66 qubit. And if you find 67, I mean, no, there is no optimal solution exists yet. And that is one of the interesting problem for quantum computing community to see whether quantum computers can give this find this optimal solution even at this very low qubit size, just 67. And yeah, in this case, so the best known classical heuristic scales as 1.34 to the power n. And we have an upcoming paper. And before that, there was a paper by JP Morgan last year showing that QAOA with the depth 12 can outperform this memetic taboo search. It's one of the best known classical algorithm. But it's just a scaling analysis, so no experiment has been done yet because of the number of gates that is needed to implement this problem. The problem is highly dense and requires millions of gates to implement it. And we revisited this problem, and we see that bias field DCQ can give better scaling. There are some assumptions are made on the runtime of the quantum hardware. It's just the scaling analysis which shows that clearly there is an advantage using quantum solvers. This will be published probably in 3 weeks in arXiv, you can find it. And another one, so I will not go into details of it because this is still, it's not open, it's not public yet. Something called combinatorial, this combinatorial reasoning for large language models. When you ask a question to a ChatGPT, it outputs a solution. And if you trace back, how did you, for this input and for this output, how did you arrive at that solution? So this follows a certain path called reasoning. So there are, you can even find it in the, what are the reasons that has been followed. It's called chain of thought. The optimal choice of reason to arrive at a correct solution is a problem that can be formulated as an optimization problem. And especially it can be formulated as a higher order unconstrained binary optimization. And this is the one thing that we are actively working, and with my team, we have developed a product. It will be launched soon through Kipu. And we did some benchmarking with the other popular large language models, which doesn't use combinatorial reasoning. And we see that there is an advantage for some hard questions that was, it was a paper by Google DeepMind, I guess, last year. So there are certain complex questions which requires reasoning. And on these questions, when we benchmark, we notice that when you formulate this as a Hubo and solve it using our solvers, so you can get better accuracy in arriving at the correct answer. And what is beyond bias field DCQ? So bias field DCQ is an algorithm that we developed almost 2 years or 1.5 years ago. And we are now extending it. So what we call the branch and bound bias field DCQ. This is a technique that is inspired from classical branch and bound techniques. And yeah, you can find this work in this paper. I'm not going into the details of how it works. And finally, what we have is what we call this sequential quantum computing. Quantum computers comes in different flavors. So there are neutral atom quantum computers, superconducting based quantum computer, trapped ions, photonics, analog, digital, and neuromorphic quantum computers. And each of these hardwares have their own advantage and disadvantage. Some are extremely fast, like superconducting or spin qubits, or even photonics are expected to be super fast. But they have limited connectivity. They have limited coherence times. So they have both advantage and disadvantage. On the other hand, trapped ions are fully connected, They have very long coherence time, but they are extremely slow. And neutral atoms are the neutral atom hardwares are all extremely slow. You can take only one sample, one shot per second. That's not at all useful for any of the optimization problems that we are tackling. So why not combine multiple quantum hardwares and mitigate their disadvantage and combine their advantages? So there we propose this concept called sequential quantum computing, where in this case we consider two hardwares. One is D-Wave's quantum annealers and IBM's superconducting quantum computers. And we also consider a trapped ion system, which is not reported here, but yeah, you can combine in a clever way multiple hardwares. So what we have shown is that standalone QA is just the quantum annealing on D-Wave. The problem that we consider is higher order unconstrained binary optimization, which requires mapping this into QBOs on D-Wave. So that results in 678 qubits. And we took around 300,000 shots, and the approximation ratio that we got is like around 96%, and the best solution is still not the ground state. And then we tried bias-filled DCQ, our own algorithm, running on IBM only, and still we were not able to find the ground state. And then we combined both the approaches. That's what we call SQC here, sequential quantum computing. Even with reduced number of shots, just 8,000 shots, we were able to get the optimal solution with this combined approach. The reason behind is that one thing is quantum annealers can be used like a warm starter. They can sample very fast, and they can tackle even problem size of 4,000, but you may not get very good solution from it. Instead of just throwing away this result, use it as a warm start for the bias-filled DCQ, run it on IBM hardware, introduce something called counter-diabatic terms, which gives you this non-stochasticity. We noticed that certain clever combination of quantum hardwares can give you results that cannot be achieved with the standalone quantum hardware. With that, this is the team. So we, what we call Quantum Manhattan team at KIPU. So basically, these are my team members who are working, and and we also have something called KIPU Quantum Hub, where you can find our algorithms, not only for optimization, we also work on quantum machine learning, quantum simulation, quantum chemistry as well. So you can find our algorithms in our website, as well as there are many use cases, applications, and quantum algorithms. You can put your own algorithm there and benchmark it. So it's open to the community as well. And also we recently extended our collaboration with IBM. So we have the right to sell IBM hardwares with our algorithms to clients. So you can also directly access different hardware in our platform, and especially the IBM hardware. And Sky Quantum Optimizer is one of the solver based on this algorithm, and you can find it in Qiskit function, IBM. And this is our team. And thank you so much. And I would like to, if you have any questions, please ask.
Thank you so much for such an interesting talk. It's always exciting to see the quantum approaches seem to work really well in your case. So, I mean, where do we even start with the questions? Any questions from the audience? Yep, please, but maybe you should use the microphone because for the recording.
Yeah, thanks for the talk. So in the first benchmarks, you said that you used 3-body terms.
Sorry?
In the first benchmarks that you showed, you said the problem had 3-body terms, right? So Hubo.
Yeah.
Can you explain again why the algorithm can handle these terms and not only quadratic terms? And also, can you elaborate on the Cplex formulation that you use for the benchmarks?
Yeah. So as you know, quantum hardware, digital quantum hardwares can directly handle 3-body terms, cubic terms. So you don't have to reduce them into QBOs, because 3-body term, there is a nice circuit decomposition that you can directly realize this on quantum hardware. On the other hand, Cplex, one has to linearize or quadratize before solving it. And the method how we did this is given in the paper itself. But here we took suggestion from IBM, who was helping us with the CPLEX benchmark. So there are multiple ways one can map from Hubo to this either quadratization or you can, which will introduce additional constraint terms as well as additional variables. So even if the problem has only 156 variable, when you map it, you will end up with a few thousands variable and constraints. So that kind of make it problem hard for CPLEX, I guess.
So that means the same problem didn't exist before in a constrained version, but you started with a Hubo, and then you gave it to CPLEX and it had to like reduce it itself, yeah?
We start with the Hubo directly, then we map it to. So it is not the other way around. So we first start with the Hubo and then map it to whatever that CPLEX solve. Yeah.
Thank you.
Thank you. And another thing is simulated annealing. On the other hand, you can directly tackle higher order terms, but only thing is the time complexity changes in the simulated annealing. Yeah.
Any other questions? In the meantime, if I may ask, so
yeah.
Usually when we talk about quantum annealing, that spectral gap, the minimum energy gap, is like one of the measures of problem complexity, right? So the small gap usually means the problem is difficult to solve.
Yep.
When you add the contradiabatic terms, so you said that, which is probably reasonable, that for many problems calculating that contradiabatic terms exactly would be exponentially difficult, right? So does it imply that sort of there might exist a class of problems for which the spectral gap is small, but calculating the contradiabatic term exactly enough is kind of okay-ish? So do we have any understanding of what kind of problems are these?
If you have a gap that is exponentially smaller, we expect that the implementation of the contradiabatic term will require exponential amount of resources. Because what you're trying to do is that you're trying to minimize or completely negate all the possible excitations between ground state and all the higher energy levels. Since the gap is exponentially small, the matrix elements that is correspond to exact contradiabatic terms has that many terms, and you have to cancel every single possible excitations. So exact CD protocol for such problem is not a practical way to go. Rather, you can look for the approximate way and then use this additional technique like bias field, and that makes it much better. But it will not completely suppress the excitation. But you can do the sampling technique and still try to get the ground state.
Yeah, so what I'm saying is that probably there is a class of problems for which computing approximate contradiabatic terms gives good enough results. And the question is, do I understand like what kind of problems are these, or is it completely difficult to see?
I mean, approximate CD terms can be calculated for any arbitrary Hamiltonians. At least the first order is we have analytical solution for spin glass, Hubos. But if you go beyond Hubos, maybe there are other Hamiltonians where it might be complex. But so far, it's a simple matrix algebra, and you can calculate at least first order, second order, third order easily, as far as I know. And as you go for higher order terms, not only the calculation, but also the implementation becomes difficult. You end up with n local term, and its implementation with quantum circuits will result in too many gates. Yeah.
Thank you so much. So
yeah, and one problem that's something called p-spin model, which is known to have a exponentially. It's easily solvable classically, but when you try to solve it with the adiabatic or quantum annealing approach, it has exponentially small gap. And even with the simple contradiabatic term, the gap becomes polynomial. It's from exponential to polynomial. Yeah, but the problem itself is easy. It's the problem of adiabatic computing, not the problem itself. So that is one example. So there is a paper saying that exponential, from exponential to polynomial gap using these contradiabatic protocols. Yeah.
Thank you. That's very interesting. Thank you.
Thank you.
Any other questions before the coffee? Then I would suggest to thank the speaker once